Good morning, ladies and gentlemen. My name is Eric Zamora, and I am a chemistry tutor at Fresno City College. And today I'd like to show you a little trick that helps me with Le Chatelier's principle. And remember, Le Chatelier's principle is when the chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. So today I'm going to give you a few examples on a specific pattern that I like to use to help me solve just different Le Chatelier conceptual questions. Okay, so start off with a chemical equation. We'll start off easy. Oh no! NH. Messed that up. Okay, so we'll start off with a simple equation. And the question asks, what if NO2 gas concentration goes up? Which way would the equilibrium shift? Now, the way I like to see these equations is first start off with a seesaw. And wherever your reaction arrows are, that's the fulcrum. And on the seesaw, there's a ball right in the middle. And it's at equilibrium, so it's not rolling to the right and it's not rolling to the left. But if the question asks, what happens to, which way will the equilibrium shift if NO2 gas, the concentration is increased? So if the concentration is increased, that's going to lift our seesaw up. Our seesaw is now tilted up. So our ball, which way is our ball going to roll? Our ball is going to roll down to the left, down towards the reactants. So if the concentration of NO2 gas is increased, the ball is going to roll to the left, making our reactants decrease. And if you notice this pattern of arrows, where one's always going up and the other side's always going down, this arrow is going to always point towards the downside. Oh, it's going to be a minute. That works. Okay. So now if we say the concentration of NO2 gas was decreased, our seesaw now is being pushed down. Our ball is going to roll to the right, and our reactants were increased. So if you notice the pattern of arrows, now if the concentration of the products were decreased, then the equilibrium would shift towards the product side, resulting in a higher concentration in reactants. And once again, remember this pattern. Notice this pattern. So now, actually, start with a new slate. Oops. Let's do a different example. We have N2 gas plus 3 moles of hydrogen gas is in equilibrium with 2 moles of ammonia. Once again, start off, it's at equilibrium. So start off by drawing a seesaw. And we have our ball in the middle. Now I know the seesaw looks a little large on the left, and you would think that it would fall to the left, but let's just use our imagination here and just keep it at equilibrium. So now the question asks, what if the concentration of hydrogen gas is increased? So our hydrogen gas is increased, so it's going up. What is this going to do to our seesaw? It's going to tilt it to the right. And which way is our ball going to roll? Our ball is going to roll downhill. resulting in a decrease in our products. If you remember this pattern from earlier, or from the last example, we have the same pattern of arrows. Now what if the concentration of the product was increased now? The product of NH3, if the concentration of NH3 was increased, what's this going to do to our seesaw? It's going to tilt it to the right. Or to the left, I'm sorry. Yeah. And which way is our ball going to roll? Our ball is now going to roll towards the reactant side. And if you remember the pattern in arrows, we keep getting the same pattern over and over. Now, the point of the seesaw is to just recognize this pattern and get familiar with this pattern instead of just jumping into, oh, remember that these arrows shift this way. The seesaw method helps you get used to establishing which way is the ball going to roll. So that's why I like the seesaw method. Now, let's go just a whole new one. In chapter 5, recall from chapter 5 that changing the volume of a gas results in a change in pressure. So now what happens if there's a change in pressure, if there's a change in volume? So probably shouldn't have erased that last equation. But using the same equation as before, if you look at your total moles on the left, on the reactant side, we have a total of 4 moles. And if you look on the product side, we have a total of 2 moles. Now an increase in pressure, this is just a side note, but an increase in pressure results in a decrease in volume. They're inversely proportional. So you always have to be careful with what the question is asking. Is it asking for an increase in pressure, decrease in pressure, or an increase in volume, decrease in volume? Now, if there is a increase in pressure, if my pressure is increased, then the equilibrium will shift towards the side with fewer moles of gas particles because my volume is going down. So my equilibrium will shift towards the smaller number. Volume goes down, my equilibrium shifts towards the smaller number. If volume were to rise, my pressure drops, and my equilibrium shifts towards the sides with a larger amount of moles.